Okay, so what we're going to do today is I'm going to try and go through simple harmonic motion here today. So this is going to be quite a long video. There's quite a bit here that needs to be done. The experiment for this one came up in 2017, 2012, 2008. Give me a second there now. The last time Hooke's law came up as an exam paper question. So last year was circular motion. The year before that was circular motion. The year before that then was, so I think Hooke's law could possibly come up for you guys. Let me see now. 2016 was the last time. So that's going to be 4 years. So I think that this year could be the year Hooke's law comes back. And you'll have to do it. So I'll go through it now, and hopefully when we get back into school, we'll be able to kind of go over it again. So I would focus on the exam papers for this topic, really. They're not that difficult. They're actually fairly straightforward. It's actually an easy enough one, really. So the first thing here is Hooke's law states that when an object is stretched or compressed, its restoring force, S, is proportional to its displacement. So, of course, you can, if you're asked to define Hooke's law, you can say this, or you can give this equation. Okay? Not this equation. Don't give this equation. It's too vague. Okay? I'd give this equation down here. All right? So, when an object is stretched or compressed, the restoring force is proportional to the displacement. In other words, if you have a spring, the further down you pull the spring, the more force you can feel resistant trying to pull the spring back up. That's basically what it means. So that you stretch something down really far, you're going to feel it trying to pull that all the way back up. That's basically it. Okay? Now with the equation here, this is kind of an important bit here now I need to point out. In the log tables, that's how it's given. F is equal to minus Ks. Okay? And just take note here, the minus sign indicates that the restoring force is acting against the extension. That's it. Okay, so in the exam, you would write it as F equals minus, and then I'd put that in brackets, Ks. So once you mention the minus, you indicate, yep, it's going in the opposite direction, but then you can ignore it. Okay, so in your maths questions, then you can, of course, ignore the minus and continue on. Okay, so the minus just means it's going in the opposite direction. So the elastic limit or the elastic constant, basically every elastic object has this. In other words, you can stretch them so far, but after a certain point, whereupon you stretch them, they can't stretch no more. You exceed the elastic limit and it breaks. That's why with an elastic band, it'll usually snap. You can extend it so far and eventually it snaps. You've exceeded the elastic limit. Or with a spring, if you pull a spring too hard and it becomes distorted, you exceeded the elastic limit, and as a result, the elastic band or the spring can't go back to its original shape. Broken, if you will. Okay, so the first question here, when a spring is stretched 6 centimeters beyond its natural length, okay, the restoring force is 8 newtons. Find the restoring force when it's 2, the extension when it's 15. All right, so start first with stating your equation. F equals minus brackets Ks. Okay, you state that, you're getting your 3 marks at least. All right, now keep this in brackets. So now that we're in brackets, we can now ignore that minus sign. We can just continue on the maths. We've already indicated this means we're going in the opposite direction. So now we can get on with our equation. Okay. So the question that's been asked is what is the restoring force, and the extension is 2 meters. So F equals F, because we don't know, and the extension S equals 2 centimeters, which is 0.02 meters. Now, we know that F equals that, so F equals K times 0.02. Okay, so clearly what we have to find is K. We have to find the constant. All right, K is a constant because it's the elastic limit of the object we're stretching. It's not going to change. And what we look back, we go back here and we're told, well, when the spring was 6 centimeters stretched, it had a restoring force of 8 newtons. Okay? So therefore, we can use that to find K. So K is equal to F over S. And we were told that when F is 8, K is 6 centimeters, which is 0.06 meters. Don't forget to convert. So when you get that, you should find your K to be, what did I get there now? I got 133 point, and then it goes 3 continuous. Now, of course, can you guess the SI unit? Look at it this way. Force is newtons. Displacement is meters. So therefore, Newton per meter. Okay? Or Newton over meter. So we have K. You simply now sub K backing up here. And what you should end up with is, for the first answer, when the extension is 2 centimeters, our force should work out to be 2.67 newtons. Okay? So you just sub that value back in up above, and you get this answer, 2.67 newtons. Right, the second question then is, what's the extension when the restoring force is 15 newtons? So everything stays the same. So F equals, oh no, hang on a minute there now. So we have the restoring force this time. So therefore, we're looking for the extension. So S equals, so let me see, F over K. Because what's going to happen is, all right, so F equals Ks. We want to make S the subject, so we divide K across, okay? And of course, that becomes 15 over 133.33, which gives us an extension of 0.113 meters. Bonus points if you can convert that to centimeters and tell me what it is. Okay, so there you go. So it's fairly straightforward. These kind of questions would be the basic stuff, the stuff that you get at the start, maybe a question 5 or something like that. Okay, right. Again, any questions along the way, please do put them up on Edmodo. Okay, underneath. I'll link this up to YouTube, and you just put your questions on the link below, underneath the link. So here we have, how do we know if a body is moving in simple harmonic motion? These can be asked as an exam question. Okay, so its acceleration is directly proportional to its distance from a fixed point, and its acceleration is always directed towards that point. Okay, so acceleration is directly proportional to its distance from a fixed point. Now, you can get away with going A is proportional to minus S here, but then you have to, of course, explain what A and minus S are, so it doesn't really save you that much time. Okay, so it's acceleration, you're better off just saying acceleration directly proportional to the distance from a fixed point in its path. In other words, as you can see down here from these balls, okay, so what you have is you have the normal length of the spring. So basically, if you have the spring, its normal length, it will be this. Okay, so the unrestrained length. In other words, if there's no weight in it, that's the natural length of it. However, if we add an object, okay, to it, it goes down to what we call the equilibrium position. The equilibrium position is, of course, the position where it stops bouncing. Okay, it's not bouncing over here, it's bouncing up and down. Okay, I'm trying to draw arrows there, but the marker is not really picking it up. It's bouncing up and down. Okay, and of course, when it stops bouncing and it's at rest, that's the equilibrium position. Okay, so it's not the natural length, it's the equilibrium position. All right, so the acceleration is directly proportional to its distance from a fixed point. In other words, here, if we pulled this ball down here, okay, that's our distance S. And then, of course, the acceleration with which it's going to fire back up to our equilibrium position is going to be proportional to it, A. All right, so the further down you pull something, the faster it shoots back up. All right, so if you have a spring at home, lightly pull the spring, you'll see it shoot back a small bit. Pull it really far down, you'll see it shoot back up really quick. All right, so they're the kind of two definitions. You don't need to draw the diagram if you're explaining it. Okay, now these here are important, these 5. They're not going to be asked, but it's kind of expected that you know them. Okay, so the equilibrium position, okay, know what that is, because they're going to talk about it comes from the equilibrium position or comes from the natural length or something like that. That's how they're going to mention the questions. Okay, acceleration and the overall force is 0. That's key. A equals F equals 0. Okay, because F equals ma, if you remember that. So if A is 0, F is 0. Okay. The amplitude, you should remember that from waves. Okay, the maximum displacement from the equilibrium position. No, remember that, from the equilibrium position is the amplitude. Okay, and of course, when you're at this position, you have max acceleration. So acceleration is 0 at the equilibrium. So the further away you are from equilibrium, the higher the acceleration goes. One cycle or one oscillation, again, if you should probably remember this from waves all the way back in fifth year, okay, is the motion of a body from one point until it's back to the same point, moving in the same direction. So I'm going to kind of draw a bit of space up here. Yeah, so what I'll do is, if you remember from waves, that's your equilibrium position. Okay. So if we start, say, here, okay, we're traveling this way, we go down and we come back up. That is your wavelength. Down and back up, okay, traveling in the same direction. But that's also one cycle, okay, so that's your one oscillation if you imagine on a wave. It goes down, back up, and back, okay? So wavelength, cycle, oscillation, they're all kind of linked here, if you will. All right. So the period T is the time for one cycle. Okay. So T is the time for one cycle here. All right. So I'll do a little bit of an explanation here. So for example, if you were told there was 10 cycles in, we'll say 20 seconds. Okay, so 10 cycles in 20 seconds. Okay, T is time for cycles divided by the number. Okay, so again, I apologize for this biro thing. I've ordered one online, but I don't think it's ever going to get here. So T is the time for the cycles divided by the number of the cycles. So here, the number of cycles was 10 cycles in 20 seconds. So it would be 20 divided by 10, which is 2. Okay, so it takes 2 seconds for one cycle. Okay, right. There's a maths question later on. We'll come back to that and we'll do that again and it'll make a bit more sense. Okay, so that's how you kind of calculate that. We'll do it again now later. And the frequency is number of cycles per second. So same kind of thing. Okay, so frequency, if you remember back to hertz and all that. Okay, so frequency has it back to, again, waves again. So they're all coming back here. All right, so simple harmonic motion mathematically is this little equation: A equals minus omega squared. S, again, the minus means that it's going in the opposite direction. In other words, the further down you stretch it, so the further down this goes, this is going to be pulling up in the opposite direction. All right, so that's why the minus is there. So again, you put the minus in brackets and you move on. Omega here is a constant. The constant being the mass and the elastic constant. Okay, so the mass and the elastic constant are the two. Okay, they're related. All right. Now, obviously, it's elastic constant divided by mass, so I should have probably put that underline here. Okay, so the elastic constant divided by the mass. Now, why is that? It's because obviously if you change the object, so if you have one elastic band and then you change the elastic band, well, then you've changed the mass of it and you've changed its elastic ability. So that's why it's the constant, okay, omega. So that derivation, the last derivation, guys, for you, all right, that you can be asked. I'm just going to check there. I think I'm right on that one. Yeah. Okay. So this is the last derivation, basically. All right. So, and this is the question: how does a system, okay? Oh, sorry. How does any system that obeys Hooke's law move with simple harmonic motion? Or how would you prove that anything that moves that obeys Hooke's law moves with simple harmonic motion, or any variation of that question, basically? Okay. So you start with this, the first equation we looked at, F equals minus Ks, but F also equals MA. Therefore, these two equal each other. All right. Now remember, we're trying to get it to A equals minus omega squared S. All right. So we start with this, and we want to get to this. That's the process. So straight away, we know we need to bring in A, and we need to make it a subject. That's why here I divide across by M, because I want A to be the subject. Okay? We want A to be the subject of the formula, so we divide across by M, and you get A is equal to minus K, and I'll roll it. So what you end up with is A equals minus K S over M. Okay? Now we know we want S because S is up here. So what we're left with is the elastic constant and the mass, which of course you have to keep constant. You see? They have to be kept constant. Otherwise, this doesn't work. And therefore, what's our constant here? Our constant here is omega. So omega squared equals K over M. Therefore, A equals minus omega squared S. And that's it. So it's a nice simple one, okay? F equals minus Ks, F equals MA. So MA equals minus Ks. Remember, we want A to be equal to everything else, so we divide across by M. Therefore, we're left with A is equal to minus Ks over M. Well, we want to keep S to displacement, so we're left with K over M, which of course, the elastic constant and the mass, which has to be kept constant, otherwise the equation doesn't work. So we sub them in for our constant, which is omega. Okay. Now this, again, so a lot of this stuff, guys, is stuff that you're not going to be straight up asked, but you need to understand and know, otherwise you won't be able to answer a lot of questions. But minus Ks is Hooke's law. Okay? That's extension, i.e. distance between the new and the original length. The natural length there. The new and the original natural length. However, for SHM, simple harmonic motion, okay, S, okay, is distance between new and equilibrium. So don't get those two mixed up. So F equals minus Ks means you have the natural length, and what's the force now pulling up against the natural length? Simple harmonic motion, we're at the equilibrium position. There are two different positions, okay? So just be aware of that. Now, this question here came up in 2012. Means it could come up again. What examples can be given of a body movement is with SHM, simple harmonic motion? Basically anything, guys. I put up as many as I could think here. A stretched spring, a pendulum, oscillating magnets, spring in a car, tuning fork, objects bobbing in water. I think that year, one year they accepted the vibrations from a fridge or dishwasher or something. No, I wouldn't say that because that's very, very specific, oddly specific, as they say. So, but any one of those two are fine. Like a pendulum and a stretched string will do, because that's basically what we already talked about. Okay, so here we go. Problem 2. So I have 2 questions here. Well, 3 if you wanted the period. Yeah, so it's a lot very mathsy for the next couple of pages, and then we'll have a quick brief look at the pendulum and then finish off the math. So we're almost done there. We're nearly halfway. All right. So the maximum force acting in a body of mass 8 kgs moving with simple harmonic motion is 40 newtons. If the acceleration of the particle is 2 meters per second, then when is this in right? Okay, so as always, I'm going to roll this up because I need all the space. Right. Write all your values on the left-hand side, down here. Find all the equations you want to, list them across the top of the page, and then try and solve. Okay, so the physics questions never really change. They're always really the same. Okay, so the maximum force acting on a body of mass, so mass equals 8 kg. Similar molecular motion is 40 newtons. F 40 newtons. If the acceleration of the particle is 2 meters per second minus 2, when the distance from the equilibrium position, so see, when it's distance from the equilibrium position, so not the natural length, the equilibrium position, so S here is going to be 0.12 meters, so the answer is given to us the question given to us in centimeters, so you got to convert it to meters divided by 100, you all knew that, of course. Right, so find the greatest distance of the body from the equilibrium position. So what we're looking for here, is S max, which I'm just going to call SM. Right, so we're looking for S max. Well, the logical equation we're going to use here is A equals minus omega squared S. S is going to equal to, and of course put that in brackets, and now we can ignore it. S equals A over omega squared. So that's obviously what we're going to use here to solve. Because we have A, we've have to find omega. So that's the equation we want to use. All right. Now we're missing two things. We can't use this A because that's not the maximum acceleration. What it says is the maximum force. So we're given something here, a maximum force of 40 newtons. If the acceleration of the particle is 2 meters per second, when the distance is 12. So when this is 2, this is 12. So this F is actually F max. All right. So I'm gonna rub out this equation here because it's just, I need all the space. All right. So what we know is when A equals 2, S equals 0.12. So what can we do with this information? Sorry. Got a few emails there randomly popping up my inbox. So when A is 2, S is 0.12. All right. So what do we have to do? Easy enough. Find our constant omega squared. Because when we find this, we can then solve it. So omega squared is equal to A over S. So our answer there should be 16.667. Now, you could leave it like this because obviously the mistake, what a lot of people do here is they find omega, they square root it, but you don't need to square root it because we don't need to find omega, we need to find omega squared. So you can just leave it as that, because you're just going to be squaring it back anyway, right? So, all right, therefore, A equals minus 16.667 S, because it's 6 continuous while it's rounded up to 3 decimal places, So that's our equation now. A is equal to minus 16.667 S. So we can find our greatest distance, because we know S is going to be equal to A divided by 16.667. Right. So I'm going to have to, do I have enough space down here? Right, I do not have enough space. I'm going to have to rub this out, So you can always record the video back anyway, all right? So the next thing we got to find. So we found a constant. We know what our constant is. I'll put it on the left-hand side here now. Now, so that's all our values we have. All right. What we need to find, inside there. So what we need to find, okay, the question is the greatest distance from the body, okay, from the equilibrium position. So in order to find S max, maximum distance, what do we say is the correlation between? So we know acceleration is proportional to distance or displacement. So if we have to find S max, so if we're at our maximum distance, what does that mean from our acceleration? If you remember, acceleration is 0 at the equilibrium position. Well, to find X max, we need A max. Okay? So when S is at its maximum, acceleration is at its maximum. Now the question also told us, because obviously we have two values here we haven't used yet, F and M. So the maximum force is 40. And we know F is proportional to A. So if you have a maximum force, what does that mean for your acceleration? It means your acceleration should be maximum as well. So therefore, F equals ma, A equals F over m. So our values are, of course, 40 divided by 8, which should give you, or at least I got, a value of 5. No, that should be a -2, apologies. Yeah, 40 divided by 8, yeah. No, hold up, I think I might have made a little mistake there. Let me check my maths. Oh yeah, I made a mistake in my own notes actually, sorry, I'm actually confused myself, yeah. Right, so there you go, 5 meters per second, okay? So we know A max now, so we'll add this to the left-hand side. AM is 5, okay? So you see, that's why you keep adding things to the left-hand side, all right? Left-hand side, you just put in your values and just add them as you get them, okay? You keep track of it. So now it's easy enough to solve, so we go back to the first equation, which we said was S equals A over omega squared. S equals 5 over 16.667. S equals 0.3 meters. So our displacement of 30 centimeters basically. So if we go 30 centimeters, we'll get the maximum acceleration. Now obviously if you exceed this, that's a question you could get. What would happen if we exceeded that? Well, you break the elastic limit, the thing would snap or break or distort. Okay. Next question then. The acceleration of a particle executing simple harmonic motion is 2 meters per second when it is 50 centimeters from the equilibrium position. What is the acceleration when it is 10? And what is the displacement when it is 0.5? Or when it has an acceleration of 0.5. Okay, so again, I need to roll this up. Write all my values on the left-hand side. Oh, I can't roll up that far, all right. So, what do we have here? The acceleration of a particle executing simple harmonic motion. So acceleration, A equals 2 when it is 50 centimeters, so S is 0.5. How do you position? What is its acceleration when it is? What is the acceleration when it is 10 centimeters? So, okay, so what we're looking for is A equals A when S equals 0.1. And A equals 0.5 when S equals S. Okay. All right, this is an easy enough one. You should be able to answer this here without me really going into it. But, so obviously we need to first find the constant. So A equals minus omega squared S, ignore the omega, the minus, omega squared equals A over S. And of course you use these two values here and you should find your omega value to be 4. Sorry, not omega, omega squared. which means we call this part 1 and that part 2. So for part 1, your acceleration should work out to be 0.4 meters per second to the minus 2. And for part 2, your displacement should work out to be 0.125 meters. Okay? Oh, my screen likes to move itself. So basically, find omega, and then you just keep subbing the values into the above equation. Okay? Because in part 1 here, we were told S is 0.1, we have omega as 4. Part 2, we have A is 0.5, we have omega as 4, etc. Okay? Perfect. Right. So, what is the relation between periodic time and the frequency? Okay? So, periodic time is seconds. Okay? The time is in seconds. And if you always forget, remember this. Hertz. Frequency is in hertz. Frequency means 1 cycle per second. In other words, 1 hertz equals 1 cycle divided by 1 second. You see? 1 equals 1 divided by 1. So 1 hertz is equal to 1 cycle divided by 1 second. Cycle per second. Cycle per second. Per being below the line. So your equations are the same from back in waves. F is equal to 1 over t, or t is equal to 1 over f. Okay? So this can kind of help you with this. Alright? So if hertz is 1 cycle per second, 1 cycle divided by second. Okay? Well then, how would you get t? Well, f is equal to 1 over t. T is equal to 1 over f. So you invert this. Okay? So 1 second, okay, would be the invert. So 1 second divided by 1 cycle. They're in the inverse of each other, basically. Alright, so this question here. A body moving in simple harmonic motion makes 10 full oscillations. So oscillation and cycle mean the same thing in a time of 4 seconds. Find the frequency. So F equals cycle divided by t, which equals 10 divided by 4, which equals 0.25. So let's imagine we don't know what t is. We know t is equal to 1 over f, so we invert that, and there we go. But let's say t then, find the period. T equals time over cycles, which is equal to 4 over 10, which is equal to 0.4 seconds. Sorry, I forgot my SI unit of hertz. You see? That's how you answer the two of them. Frequency is cycles per second. So cycles per second. T is the inverse of that. So you simply just switch them around. So time divided by cycles. That's it. Okay? All right. So making good progress. Again, any questions you have at any point in the video, please do. I think the YouTube comments are open, so you can ask them there, but I probably won't see them. So you're better off putting them up in Edmodo. All right, so we have these two questions to do, and then we're on to simple harmonic motion. Don't worry, guys, we're almost there. My horrendous radio voice, you don't need to listen to it much longer. So the relation between the periodic time and omega. So the formula for the period of simple harmonic motion is important to be remembered, but it is not necessary. You do not need to prove this. Okay? So in other words, t is equal to 2 pi over omega. Okay, so if a particle moves simple harmonic motion, whose equation is a is equal to minus omega squared s, then the period t of the motion is given by t is equal to 2 pi over omega. Okay? So period is equal to 1 over f, but if we're moving in simple harmonic motion, 2 pi over omega. Now, I don't have my log tables with me, but I think that is in the log tables, so you don't have to learn it off either. Right. So these are from page 150. So when the displacement of a particle executing simple harmonic motion is 12 centimeters. Note they'll always give you in centimeters, so you better get good at converting. S equals 0.12 meters. And the acceleration is 2 meters to minus 2. Find the period of the motion. Well, t equals 2 pi over omega. All right? So we need to find omega. go to your log tables, find the equation with the one missing value. A equals minus omega squared s. And there you go. Okay, so you should be able to work that out. Again, ignore the minus. All right, so put it in brackets and away you go. All right, so I don't need to do that out, but you should end up with omega being 4.08, and you should end up with t being 1.54 seconds. Okay, so you should be able to work it out from there, from these two equations. That's basically what you do. List your values, state the equation they want you to use because they're asking for the period. Okay, so it has to be this equation. We need it, omega. Look for the equation with one missing value. It's that one, and away you go. Problem 6. So A equals minus, or A equals minus 23.6 s is the equation of motion of a body moving with simple harmonic motion. So A equals minus omega squared s. So that omega squared equals 23.6. You see? So calculate the period of the motion. Oh, well, in that case, the period of the motion, t equals 2 pi over omega. So therefore, omega, we have to square root that. Where's my calculator there now? So I got 4.86, which means this becomes 1.29 seconds. The number of oscillations it makes per second. Number of oscillations per second. Okay. So number of oscillations per second is same as saying cycles per second, which equals hertz. So F equals 1 over t, which is equal to 1 over 1.29, which equals 0.775 hertz. Took me a second there. All right, so for that one, the number of oscillations it makes per second. Think of it, number of oscillations per second. Oscillations per second. What's another word for oscillations? Cycles. Cycles per second. What cycles per second? That's hertz. Okay? If you'd forgotten that, could you answer it? Let me see. Well, yes, you probably would be able to figure it out anyway, because what you would say is if the 1.29 seconds, okay, so how much for 1, okay, so 1 would be 1 divided by 1.29, okay, to find out how much 1 cycle. Okay. Right. So here we go. We're almost there. So we're on the last bit. And then you basically have the exam paper. The exam paper question came up in 2017. So 3 years. There's a chance it could come up again. I might do a short video on that, but there's not much really there. You have the notes. You have past exam paper questions. It's not an overly difficult one. It's a nice experiment to do, but obviously looks like we're not going to be able to do it. So the simple pendulum. All right, so this is where Hooke saw most often falls. All right, so a pendulum consists of a light string with a mass at the end called the bob. The length of the pendulum is the distance from the fixed point, from a fixed point to the center of the bob. Okay, in other words, the length is from here to here. No, that's not the center of the bob. To here. That's L. Okay, so it's from the fixed point to the center of the bob. Okay. All right. So what we have here then, right? So I'm gonna highlight the important bits here just for you. You can copy them at home. All right. So the bob is moving, swinging. It's swinging over and back A to C, as you can see. Okay. So time taken for the bob to go from A to C and back is the period. In other words, over, back, and then it stops for a split second before it goes back again. That's the period. Over and back, and then it goes again. Okay. The amplitude, okay, is the maximum displacement from the equilibrium position, which here, of course, is B, okay? Meaning the amplitude, the equilibrium position is B, by the way. Meaning the amplitude of the pendulum is A and C, okay? And the key here is, although the amplitude decreases due to air friction, the period actually remains the same. So although the angles keep getting smaller, okay? The period, the time it takes to go from C to A to back actually doesn't change. It stays the same the whole time, okay? Now, of course, you would be doing that. I think some of you did it actually on the revision day, but hopefully if the schools come back, we can get you in, maybe if you want to try and go for that one again. Key as well is this question here. You need a small angle swing. Too large an angle creates movements. It starts to move in circular motions. It needs to move in one plane only. If the angle is too large, what happens is it starts to swing in a circle, and then of course throws it all off. All right. What is the relationship between the period and the length of a simple pendulum? That is a common exam paper question, okay? And it's fairly straightforward. You look at the equation being T is equal to 2 pi square root L over G, all right? So what's the relationship between the period and the length? They're proportional, okay? T is equal to the whole, but it's proportional to each individual part. So T squared, So T squared is proportional to L, or T is proportional to root L, and T is proportional to root 1 over G, or T squared is proportional to 1 over G. Now, you should just be aware of that. In the graph for the exam paper, for the experiment, that's what you use. Or, sorry, not that. You can use this, sorry, let me rub that out. All right, you use this one. You square your T and away you go. Well, you can do this as well. You can, of course, use the T proportional to root L, but it's a little bit more awkward, the squaring the L's. It's a lot easier to just square the T away you go. Okay. Right. So that's your relationship. T squared is proportional to L, or T is proportional to root L, either one. They won't mean the exact same thing. All right. Now here, this question comes up quite often. What is the acceleration due to gravity on the moon using a simple pendulum, or on the planet, or on the planet Earth? Okay. So what you can do is this isn't in the log tables because it doesn't need to be, you can give that equation. So you can start there, G is equal to 4 pi squared L over T, okay? It's basically the previous equation, and you rearrange to make G the subject. All right, so to save time in the exam, now in the exam, you don't need to do it. You could start with T is equal to 2 pi square root L over G, square both sides, rearrange, and away you go. Or to save time, which is what I'm going to do in these next few questions, you can go straight to this and do it from there. Okay, they will give you the 3 marks for the equation because it is the exact same equation basically. It's just rearranged. That's all. Right. So problem 7. A pendulum of length 80 centimeters has a period of 4.44 seconds on the surface of the moon. Calculate the acceleration due to gravity. So L is equal to 0.8 meters. Write all your values. Time. A period, so not small t, my apologies, my mistake there. So period is a capital T. 4.44 seconds on the surface of the moon. Calculate the value of acceleration to gravity, so G equals G. So again, you can give the regular equation and work it out, but I'm going to save time and I'm going to give this equation, okay? So G equals 4 pi squared L over T squared. Okay? You can start with T is equal to 2 pi square root L over G, and you'll eventually, when you work it all out to make G the subject, you'll get to here anyway. Okay, so don't worry too much about that. I got my G value to be 1.66 meters per second to the minus 2. So when you sub in your values, that's kind of what you should get. All right, so problem 8. A simple pendulum of length, so L, 0.8 meters, makes 50 oscillations in 90 seconds. Okay, find the value of acceleration. So we need G. and we need to find t. Okay, so t, what did we say t was again? Number of oscillations, cycles per second. Hertz is cycles per second, so this would be time over cycle. So 90 over 50, which 1.8 seconds, I think. Yeah, 1.8 seconds, okay? So time, so frequency is cycles per second, okay? So frequency is cycles per second, which is cycle divided by time. So therefore time, our period has to be the other way around, okay? Time divided by cycles. So t, 1.8, and g equals 4 pi squared L over t squared. So g, I got here to be 9.75 meters per second. So you should begin to see a trend. The extra step is usually find this first. Okay. And last but not least, what is the length of a pendulum? Okay, so t is 2 seconds. G is 9.8. And we want L, which equals L. So this time we're rearranging it differently. T is equal to 2 pi root L over G. T squared equals 4 pi squared L over G. So let me see, we want L, so that means G has to go up. So T squared G all over, because this has to be multiplied up and these have to be divided. So that becomes 4 pi squared equals L. Okay. And we sub in all our values and we should end up with 0.993 meters. Did I do that right? Square both sides, so we get t squared equal to 4 pi squared. We divide across by 4 pi squared. We multiply across by g. Yeah, I think that's right. Okay. So these are a few exam paper questions you can have a look at. Let me grab my notes there for 1 second. Right, so the year that it came up, other than those, was... So 2016, explain simple harmonic motion, state Hooke's law, and then give the derivation, use Hooke's law to show that mass executes simple harmonic motion. So 2016, question 6. Let me see now. Similar stuff again. The second part is the time taken for each oscillation. T is equal to 2 seconds. The weight of the bob is 3.5 newtons. It travels a distance of 18 centimeters during each oscillation. So there's a little bit of a few extra steps there, but it's nothing you haven't seen before. It's actually fairly straightforward. Calculate the maximum angular displacement. That's a little bit tricky. Okay, but I have my notes up, so have a look at that. So that bit's a bit difficult. Drawing the forces acting on it it's okay. Yeah. So 16. Let me see. 15, circular motion again. 14 was vectors. 13, circular motion again. Yeah. 12, circular motion again. That's the angular velocity, circular motion. And 11, moments. 10, 2011, yeah, it's up there. So basically, guys, I think Hooke's law could come up for you this year. So have a look at 16, 14, 11, and 9 exam paper questions. 16 is tough, actually. It's a lot tougher than 14. Question 12A. Let me have a look at that one. Yeah, that's very straightforward. The question 12 questions are never overly difficult. Same with 11. I think I missed one there. Question 12. No, that's fine. Yeah, so the question 12s are always easy enough. Yeah, it's nearly every year. 2011 question. Yeah. Yeah, so I think it could come up for you. Because circular motion is the one they love to ask for higher level, because circular motion they can make very, very difficult. If Hooke's law does come up, I wouldn't worry too much. If you answer those these 1, 2, 3, 4, 5 questions, you'll basically have answered every kind of Hooke's Law question they can really ask. Have a look as well at the mock exam papers that I put up as well. There might be a few extra questions on that. Okay, so if you have any questions on this topic, please don't hesitate to put them up on Edmodo, and I'll get back to you as quick as possible.